Okay, we'll start with this. First of all, coming down here, one of the things I've done is I highlighted the area where we are tonight. And one of the things that I thought I'd do is, considering the huge amount of material. Well, first of all, somebody suggested filters, and I'm thinking, oh, okay, what a great topic to study, but everything from simple to a little overwhelming. But just in case you want to pursue any other topics, you know, yourself or, you know, I encourage putting things together so that you folks can help other folks. You know, a lot of times we get so wrapped up in our own stuff, you know, how easy it was for us. We fail to realize how difficult it is for some others, right? So here's what we might do. If you ever want, there's outlines, all right? Here's an outline on just power supplies. You know, there are, shall we say, a few things to consider on just power supplies. By the way, if you want, even though this is an HTML file, I can make these available as PDF. So if you ever want to, let me know, because they started as PDF in the first place. All right, going back here, here's one on vacuum tubes. You say, well, we don't use vacuum tubes anymore. Oh, I beg your pardon. We sure do, a lot of places. By the way, one of my favorite Kenwood radios is the 520, and it's tubes. Okay. So questions here, all right?
Yeah.
Go back here again. You got, by the way, you got klystrons and magnetrons and photomultipliers, and you got TWT tubes and things like that. A lot of good stuff. Then you got amplifiers. Well, in amplifiers, you got the various different classes of operation, A, B, C, D, and etc. Voltage divider bias, oh, you got transistor types as well. So, and anyhow, there's a whole lot of stuff in here. And let's go back again. Here's oscillators. Now, back in the days when I was taking the test to get either advanced or extra, I had to be able to identify various different types of oscillators. That was some of the test questions. I noticed it's totally devoid of all that now, but you had to know how to identify any one of these different oscillators here. You know, Hartley, Colpitts, Butterfly, Franklin, whatever. And then you got various different types. We're going to be discussing this bridge T or the twin T oscillator tonight if we have time. So anyhow, go on down from there, and lo and behold, here is filters. And I highlighted some of the things that we'll be talking about tonight. There's a lot of stuff on here. And by the way, coming down here at the bottom, special types. These are ones I'm really not qualified to talk about, but I know about them. M-derived, constant K, Bessel, Butterworth. Of course, then there's the crystal filter, and then mechanical filter, which was made by Collins. And I have tracking filter, which is not a well-known one because that was a very specialized filter that we used at the Space Center when we were doing frequency analysis of telemetry from missile liftoff and stage separation. So, by the way, anybody know how they did stage separation in a missile? They have squibs, explosive bolts that separate the two stages. In other words, they fire those bolts, and then that one just had nothing holding it on, so it falls away.
Oh my God.
That's how they did it. However, one of the problems that they were concerned about, that sends a shock wave clear up through the system, and it may even go clear up into the payload. And guess what? It did. And they were really concerned about how much that shock wave went up into the payload. So we did a lot of testing. That's what I was involved with a lot, was analysis and then looking at the data off of the vibration tables. And in fact, well, that jumps track. I better drop out of that.
Can I ask a question?
Fire away.
Well, Dave, so you said the shock came all the way up.
The what now?
You said the shock would vibrate itself all the way up into the payload. Good Lord.
Yeah.
From the explosive bolts, and yet it was more so than the rocket shaking itself?
Oh, no, it was just one of the factors that they had to be concerned with.
Wow.
But the vibration, of course, you know, you hear a lot of noise. And of course, that noise has a lot of energy to it. And that energy would transfer to the system. And one of the things they were concerned about was the resonances. They had some unexpected resonances that they had to deal with. And so they had to put some real dampening on that camera door to keep that from being a problem during liftoff. Okay, now one of the things we're going to be doing here is we're going to look at this circuit here in detail after a while. But before we do this, here's something that I would like to state, and that is that in order to really understand these different filters, different types here, it is my opinion, you really need to consider sooner or later, you got to get back into reactances, because reactances is a core part of all this. And I'm going to spend about 20 minutes on just certain aspects of reactance. Here's also a curious thing as well. While we're discussing the reactances here for filters, as it turns out, all of the material that we'll be talking about has a subtle relationship with antenna concepts. And whether we'll have time to get into that, I don't know. But I think as we go through it, if you have that in mind, I think you might be surprised. Okay, now, in the reactance considerations, we're going to look at this. Now, this is my talking points, so to speak, okay? Now, I have this so you can bring it up later because we don't have time to go through all of this. I'm not going to go through this in a piecemeal business because I have something else involved as well. Another one here, which is talking points. And by the way, these are all available for just clicking on them. You'll notice that this page here is talking points, but with links. All right. One of the things I want to point out right off the bat is this. This was actually a test paper, a quiz paper I made for my students years ago on op amps. But I want you to look at this particular drawing right here, figure number 6. This is a low pass filter, meaning that there's a roll off at some point in time. And then here's a high pass, which has a roll off here, but then it continues on. And from there on, it's good conduction. And then, of course, this represents a bandpass filter. This guy over here is a bandpass reject. Now, this is a fundamental drawing. However, I want you to keep in mind that the bandpass here can occur anywhere. So that's adjustable. It just depends on how you design it. You can have a low pass filter that can extend clear up and overlap a high pass. And if it does, then the two of them together, guess what? Will make a bandpass. Now, one of the other things we're going to find is that a bandpass filter and a bandpass reject are actually the same filter, but with a different application. And we'll get to that later. All right. Now, to do all this, let's back up and start with this. Coming into this area here, this is where I want to spend most of our time tonight. First of all, in terms of reactance, there are 4 things you want to consider on reactance. If you're going to take notes, for instance, there are 4 key words. First of all, energy is a key word on this because what happens, inductors and capacitors store energy. That's a key factor. We got to get this across. And if you're teaching someone else, if you don't do this, then this is the whole point. You got to say, look, an inductor stores energy in an electromagnetic field. A capacitor stores energy in an electrostatic field. Then what you're also going to find that the way they get that energy is they absorb it. So the inductor absorbs energy and a capacitor absorbs energy. But then, of course, they can also discharge that energy. And I think you have to get this point across to any newcomer if he's going to understand a lot of the other concepts we run into in the circuits. Here's what we also do. An inductor does not like changes in current. Capacitors don't like changes in voltage. So what you've got here, if you come in here with a voltage, here's an interesting thing. A capacitor is for the first instant of time a dead short. Now, I emphasize that for a moment because what we do here is that means a dead short will draw current while it's charging. And you know what? The coil doesn't see any of that. because the coil at the first instant is an open circuit. Now, as frequency goes higher and higher, which is the rate of change, and that is another one of your very key words. If you don't have that word in there, rate of change, you're missing part of the picture. So what you're saying is that rate of change is really, guess what? Frequency. Hence, we have our formulas, which are 2 pi FL for the inductive reactance, how this reacts to a change in current. You see, you got to get across to this individual where this is a new thing for them. I don't know, if you guys look back, if you helped anyone else, you probably have noticed that there are certain areas of electronics, they have a lot of trouble absorbing, okay? And I think this is a major one right here. Inductance, reactance of that inductor, reactance of this capacitor. Now what happens here, if it's a dead short, you're going to have current. Well, current is a flow of electrons. And as a flow of electrons accumulates here, it builds up an electrostatic field. Notice I'm emphasizing the field, electrostatic field. And what happens is, as this capacitor is charging, I've got positive sign here, but the thing of it is current is still going to flow. And by the way, DC, this is an open circuit. At DC, this is a dead short. So if you put those together, now what you've got is this. As the voltage tries to rise, this capacitor says, not on my watch. So as a result, it draws current, and drawing current is absorbing energy in the electrostatic field. The interesting thing too is everyone who's ever worked in a electric shop or electronics shop, TV repair and such, like Walt and I have talked about this, where you charge up a capacitor and you leave it laying on the bench for some poor soul to pick up and put their fingers across it. And it can be interesting. Everybody collects around when they know what's going on. However, an inductor is an entirely different thing. One of the things I want to point out is that all treatment of the inductor is exactly opposite from that of a capacitor. Or if you wish, anything you learn about an inductor, the capacitor is exactly the opposite, except for one thing. They store energy because they absorb energy. Now, going back to this other business, look here. This is obviously the pulsating waveform, as best I could draw it, coming off of the power supply. Now, what happens is as the voltage starts to rise, remember one more thing, you got this diagram, but this is not just a diagram of voltage, this is also a diagram of current. And then you start really bending somebody's mind when you say, wait a minute, if this is a dead short, what's the voltage across the dead short? 0. But wait a minute, there's a lot of current. Now you begin to teach the fact that current can be an independent identity to the voltage because it has to do with the ohms that's involved here, right? So as this guy here is charging, reaches on up like this, and by the time it gets up about there, the coil at this time is starting to say, well, maybe a little bit. However, when you start down the other slope, what's going to happen? This charged capacitor does not like changes in voltage. So what does it do? It starts to dump. And when it starts to dump, it's going to go right through this coil. So the current through the coil will increase while the capacitor current decreases. So going back to the beginning, at the first instant here, as the current, or I should say, as the voltage starts to rise, this guy here acts like a dead short. This guy acts like an open circuit, no current. However, this guy here says, I'll take it all. So as this guy here starts to charge up, then we understand that the collection of electrons on this capacitor is what represents the electrostatic charge. And that electrostatic charge will be fine if you disconnected it. But since it is connected, when this voltage starts to drop, this capacitor will start to discharge. And as it discharges, it's going to have current that goes through this guy here. Don't worry about the polarity because I'm just talking about the essence of the current flow. Now, here's another thing. There is a rate of change that is very particular in this area here. The engineering staff, if you want to look at it this way here, has a formula for this, and they say the voltage developed as the magnetic field collapses depends on the rate of collapse, and they have a formula that says E is equal to the change of flux versus the change in time. E phi dt is the correct formula for it. By the way, the two bars, iron core, if they were dashed or dotted, then that would be like powdered iron core. And when you get up into RF, you don't want either one, maybe a powdered, depending. But what you'll do then is this would be just the core by itself. There's a whole lot of things involved in this, and there's one other term that comes into play on a coil that does not show up over here. How does this guy here resist current flow? What happens is as the voltage rises and as we try to make current flow, the energy that's in the current flow develops what's called a counter EMF, CEMF, and the CEMF opposes the attempt to shove current through it. So what happens is if you got voltage to voltage matching it, guess what? No current flow. So what happens is the faster you try to make it go, the more counter EMF there is. Something else that we need to look at. If you look over here, the rate of change here is greater than here, and greater than here, and greater than here. And finally at the top, it's rolling over the top. And what is our rate of change up there? None, zero. So at that point, what is the counter EMF being developed at that point? Nada. So one of the things we can look at, if we had time to do so, because in the classroom, I would spend several days on this entire topic here, because we would draw graphs of what the counter EMF is as this voltage here and the current is changing. All right. Now, there's something else that's important here. Let's say that you're a new beginner and you want to experiment with a power supply so you know how it works. So you put together this really basic circuit and you put in a good sized capacitor here and you got it ready to go. You turn the power supply on and pop goes the fuse. And you think, well, that's strange. So you replace the fuse and you turn it back on again. The moment you turn it on, pop, it blows the fuse again. What is going on? Remember what I told you? This guy here is a dead short. And as a dead short, it can draw lots of current. So you put in a bigger fuse, not knowing any better, and you turn it back on. And this time you wind up smoking the diodes. Oh, well, maybe I should do something different. Guess why they do this? They put a resistor in series with this so as to dampen the surge, and that's called a surge resistor. So they do this to reduce the surge. Now, there are other considerations. By the way, this is called a capacitor input filter. You say, wait a minute, how come we got a connection here and a coil here? Why isn't it inductive? Well, because the capacitor being a dead short doesn't even allow the inductor to take place. It has to be timed in this line here. So it becomes in the circuit, but a little bit later on. However, down here, you have the same two components, but this time you have the inductor in series. Even though this is a dead short, this guy here is, what's he doing? He is restricting the amount of current, because what happens is as the current builds up, it is the current that flows that causes the electromagnetic field. So as the current flows, the more current builds up more energy. There was our key word again, energy, energy, energy. There's energy in the electrostatic field. There's energy in the electromagnetic field. And here you've got energy in the electromagnetic field. And finally, when current begins to flow, guess where it goes first? Not to the load, but here. However, between the two items, be they here or be they here, we'll take these bumps and begin to straighten them out. Now, the most common circuit, of course, would be like a pi filter. And we don't have time to get into that, but I just wanted to point out our main key words: storage of energy, absorbing energy, discharging energy. And the same thing here: absorbing energy and then the electrostatic field, and storing it, and it'll keep it even if you disconnect it. But that's not true here. You disconnect this guy here and that field collapses so fast that you may only have 12 volts here, but you can easily develop 12,000 volts coming off of this guy if that magnetic field collapses real fast. After all, that's how the car spark coil works. Collapsing magnetic field. I've got another drawing we can bring up after a while. All right, keywords: rate of change. You know, here's your fastest rate of change. Now, if this is only 120 hertz, what happens when you go up to higher frequencies? Let's say you go up to a kilohertz. Up to a kilohertz, you have a faster rate of change because this whole thing is happening much, much faster. Everyone with me so far? Now, I'd like to back out of this for just a minute and do something else. Electrical safety. There's something that not everyone knows, and I will assume that you guys probably do, but nonetheless, I want to put it in here for the record. 60 milliamps is enough to cause severe cramping, so you cannot let go. 100 milliamps, I'm talking about arm to arm, hand to hand through the trunk, can be lethal. They consider that 200 milliamps through the trunk is lethal. Now, what's more dangerous, 110 volts AC or 110 volts DC? 110 volts AC is more dangerous than 110 volts DC because the 110 AC can cause irregular heart rhythm called ventricular fibrillation or heart flutter. Now, if you went up to a higher voltage, let's say 220, 440, higher voltage can cause your muscles to cramp, your chest to cramp, and even stop your heart from beating. There is a better than 50-50 chance that your heart will start again if you can get off of that circuit soon enough. That's a given. I think God has built that into our heart so that it actually will do that, okay? Just a factor. Now, one of the things that I've also found is kind of interesting. I used to, well, you know, if you're in a supervisory position or an instructor, you have to take CPR every year or two. And whenever they conducted the CPR for certification, I was asked to come in and do the electrical part. What I would do is I would take a power supply and an ammeter and hook it up to a flashlight bulb. And I'd say, okay, when you first start to see that bulb filament light, just glow just a little bit, then pipe up and let's take a look at it. And invariably, it was enough to kill you. And they were surprised. Here's a 3-volt flashlight bulb. And I said, okay, what's more dangerous, current or voltage? Which kills you? It's the current. Now, here's something that you may not know. The epidermis, on the, which makes up your skin, if you will, has 2,000 times more resistance than the inner body does. Normally, if you go hand to hand with an ohm meter, you'll measure about 200,000 ohms. If you happen to puncture yourself and measure the inner body, it's only 200 ohms. Big, big difference. Also, let's look at this. You know that being wet when you're getting shocked is more dangerous, but how about if you're sweating? Oh, that's a lot more, because now what you've got is sweat glands. They're putting out salt. And that salt is very conductive, and it isn't topical, if you will. It is lots of places, and therefore can be much more dangerous. Also, something else, just trivia. Did you know that the epidermis is transparent to infrared? Meaning, if you're standing out in the sunlight, bright sunlight, that infrared light from the sun heats your inner body. Just a little bit of trivia there. Comments or questions? Let's go on. All right. here's a chart that's important. This chart here, I don't have numbers on here because numbers are basically irrelevant. This point is DC, and therefore, guess what? 0 ohms reactance. And what's interesting is an inductor, as you increase frequency based on this formula here shows the linearity, 2 pi FL. As you come up in here, there is more and more ohms. So this is X sub L equals, and that is this guy here. And this depends on the number of henries. Now, more henries would come up at this angle, less henries, like in the millihenries, the millihenries or the microhenries would be down here. As far as capacitance is concerned, this loop that's here will either blossom out or blossom in, depending on the amount of capacitance. Now, anybody know what the definition is for 1 farad? I usually tell students 1 farad will hold 1 coulomb, by the way, 1 bucketful of electrons at 1 volt. Just a little bit of trivia there. Henry, 1 Henry will develop a counter EMF of 1 volt per Henry per amp. In other words, if you have 1 amp, well, just a second though, that's wrong, isn't it? Think about it. I said change. You see, if you change 1 amp per second, in other words, you go from 1 amp to 2 amps in a linear fashion, 1 Henry will develop 1 volt counter EMF during the entire second. It'll hold 1 volt at that change. If you change the time and make that a millisecond, it'll develop 1,000 volts instead of 1 volt. Now that's the definition of a Henry. By the way, 1 coulomb of electrons traveling along a wire in 1 second constitutes 1 amp. You know, what's interesting, what I found is that a lot of times we never stop and think about what those measurements actually are. Now, going back to this, where capacitance intersects inductive reactance, at that point, that will be resonant because the inductive reactance is equal to the capacitive reactance in ohms. Oh, and by the way, if this happens in a power supply, it will play havoc with your regulation. You don't want your filter circuit to be resonant at 120 hertz or 60 hertz or whatever is the frequency of your power supply, because suddenly your power supply is no longer a power supply, it's an oscillator. And by the way, we actually ran into that problem at the Boeing Development Center one time when they were building some special power supplies for some laser systems. Kind of an interesting problem to have, wouldn't you say? Okay, now that we've done all the simple stuff, shall we get back onto some of the more fun stuff? Any questions so far? I know all this sounds like trivia, but I think it's kind of neat trivia myself. Good review, if nothing else.
Yeah, that's excellent.
All right. All right, here we go. Let's look up this guy here. Now we can say, okay, we've done that one. Let's back up here. And, before I forget here, well, we're going to do this one here. We did that guy already. I highlighted him so you could consider that. And now let's see, going back here. Oh, I know where I'm going. Here we go. Now we're into the fun stuff. Now, some of your filters are only one inductive component, like capacitors with resistors. Now, here is a key thought. At DC, this is an open circuit. However, as the frequency goes higher and higher, this becomes more and more conductive, and therefore, guess what? This will cut out your higher frequencies. So therefore, this becomes a low pass filter. All right. Now, in that same respect, here was one that people have used for, years ago, when you had a turntable with a 78 RPM player, or record rather, and it had noise, scratches, if you will. Well, you could take this guy here, and by adjusting the resistor, you could determine how much this capacitor shorts out the hiss on the record. All right. Now, let's go to this guy. Here we go. At DC, this guy here is a really good conductor. But as the frequency goes higher, this becomes an open circuit. So guess what we have? This is still a low pass filter. This is a low pass filter. Here we use the filter to short out high frequencies, and here we just don't allow them to come through. The difference on this guy and this guy is the fact here you have a common ground, and this might be a piece of coax that's connecting these together, miniature coax. On this guy here, this is balanced. It really is the same principle as this one here, but it's balanced. Now comes the question, why would you have a balanced here and unbalanced over here? I'll give you an example. At the Space Center, when we were taking signals off of the shaker table, these signals are down in the millivolt range, and they're like 80 yards away. And as the cabling, or I should say the data, is shipped up to us where we're analyzing it, you can pick up a lot of signals that you don't want to come into your situation. So by having a balanced one, you'll feed this into an amplifier over here with balanced inputs, and therefore, and besides having a twisted pair of cables, the information that comes in here, you're looking for the difference between these two. So if this one here goes high and this one here goes low, you're looking at the difference. But in a hostile environment, you might have both of them go high, both of them go low. And by having a balanced line coming into a balanced amplifier, you discard, if you will, the comparative difference. All you're looking for is the difference between these two. All right, let's come into this guy over here. This guy here is just the diametrical opposite of this guy. Here's a high pass filter. Why? Because at low frequencies, that's an open circuit. And as an open circuit, no signal. From input to output, no signal. But at some point in time, this begins to conduct. And as it begins to conduct, then the signal starts to come up. So it takes a higher frequency for this guy here to conduct. Otherwise, it's an open circuit at low frequency. I'll take this guy over here. Here we have at low frequency, he's a short. Now look at the difference. This guy here is an open at low frequencies. Here it's a short at low frequencies. What I'm trying to point out then is that you can have a high pass filter as a series type or a parallel, shall we say, killer. So you can go series or parallel, either one. And here's our balance circuit again. And over here, you have to have a frequency high enough to pass through these two guys here. And as Walt would point out, then in certain circuits, you would wonder, getting these values to a certain area, or a certain, say, value, so as to have a impedance match, so as to get the maximum signal you want. Now let's come down to this guy here. This guy here is typical for a power supply right here. Power supply normally has a capacitor here, and the inductor there. And by the way, in the lab, if you build this circuit in the lab, you'll find that this capacitor here affects the overall output surprising amount compared to this guy. Well, that's because of the way it's following this inductor. Anyhow, this is a typical one. However, something else that you do, if you ever build a power supply, you have to put a bleeder resistor in there, because if you turn the power supply off, these guys will remain charged unless you've got a load sitting out here. If you don't have a load, you can have a very dangerous situation. Like, you know, back in the days when I built a power supply for tubes, for tube radios, this was like 450 volts here. not something you want to put your fingers on. So if you turn the power supply off, you want it to, shall we say, bleed down so it becomes safe. Okay. Now, here's where we get into something really interesting. Now, this is where it really gets, shall we say, mind blower. All right. One of the things we found is that a capacitor, remember, is diametrically opposite than an inductor. And so is the phase. They're 180 degrees out of phase, which means, while the capacitor is drawing current and charging up its energy in its electrostatic field, the inductor is sitting over here doing nothing. However, when the capacitor dumps, it will dump back in through this guy here as well as through the other circuit. Now here's the key part. If it turns out that the capacitor reactive value in ohms is the same as the inductor value in ohms, this is called a tank circuit. And what happens is you have what's called a flywheel effect. You'll have current oscillating back and forth, back and forth, back and forth here. And what happens is at this point, at that critical point, there is no current flowing through this leg or this leg here. It is all inside the tank. And since it's all inside the tank, this becomes an open circuit at resonance. So this is an open circuit filter. Now, bandpass comes into play. And by the way, bandpass brings into another technology word called pass band. And pass band is that band of frequencies that will pass through a bandpass. That's the description of it. Over here, we have a whole different scenario, but is the same thing. This one here is parallel, therefore it's a tank circuit. This guy over here, oh, he's way different. The coil and capacitor, if they are the same ohms, becomes a short circuit. At lower frequencies, current would go through the coil, but at low frequency, this is an open. At higher frequencies, the coil here becomes open and the capacitor says, well, I'm ready. So what happens is only when the two match each other, ohms for ohms, is the circuit going to be a bandpass filter. Now notice, if you will, I have a series bandpass filter here and I have a parallel bandpass circuit over here. Now there's another interesting thing. If I take this tank circuit and I put it here in series, instead of being a bandpass filter, it's a bandpass reject, because at that frequency, nada, nothing, no signal gets through at resonance because it's too busy here and creating an open circuit. So now you have a trap. It's a bandpass reject, which is called a trap. Over here, I have my series resonant circuit, which is bandpass. But if I put it in series, it's a bandpass reject, because at resonant, this becomes a dead short. Now, there's another factor that comes into play. You'll notice I have a resistor here and I have a resistor here, variable. There is a factor called Q, and Q is short for quality. The question is what is the quality of this circuit? And is there anything that would affect the band pass? And then, in other words, the band width, if you will. And the answer is yes. Q is equal to, and if you want to put this in notes, Q is equal to X over R. Now, a coil is going to be a coil of wire or a conductive element, but it still will have a certain amount of resistance. And when you get up into RF, this coil might be a small tube. And in fact, if it's high enough frequency, and if you really want quality, you may have, it's a hollow tube, but it has silver plating on it. That's because of what's called skin effect, if we have time to get into that. So what happens is, as you introduce more resistance, you change the Q, and that will affect the bandwidth. In that same respect, you could adjust that here in this one, because this resistance is here. As you add more resistance in, you're lowering your Q. And the Q factor will have a deliberate effect on the bandwidth, or what you could call the pass band. Now, here's a whole nother story. Now, this is one of Walt's favorites here. This is the attenuator, where you have a calibrated attenuator where you want to have the signal coming out as a dB factor of what the signal is coming in. So you can use this on the front end of a receiver, for instance, and still have it balanced and have it matching your setup to where the signal is so many dB less. Like, for instance, on my Kenwood 599 series, you had a stepped attenuation where you could kick in a 10 dB attenuator. Well, you don't want reactance in this circuit. You wanted a pure resistance. Can the circuits get more complicated than this? Oh, yeah. But I've just tried to put what I call walking points or talking points up here. Q, quality. If you have an antenna that's a high Q antenna, that means you deviate from the center frequency and your SWR goes up in a hurry. Whereas if you have a low Q antenna, you can operate over a wider bandwidth.
Is that why magnetic loops, Dave, are so touchy as far as tuning them?
Yep, I would say so. However, at this point, I say I'm not qualified to discuss that. Now, going back just a little bit, when we analyzed the telemetry coming off of the missiles during liftoff, what we would do is the tapes that we worked from, the telemetry tapes, were like 2 inches wide and there were 14 tracks. What we do is we pick a particular time that the engineer wanted to sample, and we would cut a loop of tape and run it through a machine that just runs the same loop over and over and over again. And then while that tape was looping around, we would run what was called a tracking filter, and it would look at a certain bandwidth and a certain pass band, if you will, as you would take the filter and run it through a range of frequencies. So this particular very expensive filter could be controlled by voltage, but more often as not, we had a signal source that we would put into it, and it would follow the signal source for the frequency that we were interested in. And then what we did is that's how we determined what energy was being transmitted from one end of the missile to the other through the skin or through the innards in some cases. And you know, a lot of things come into play, like even couplings. So, and then that filter could be set for, like I say, a particular bandwidth. But what would happen is that bandwidth would travel from low frequency to high frequency as this loop of tape was going around and around. And then we had a plotter, so that the amount of energy that showed up would cause a spike at that particular one, which represented the energy for that frequency on that part of the liftoff. It was an interesting thing. Oh, and by the way, having analyzed the frequency, then what you want to do, of course, is you want to test the payload on the shaker tables. And the shaker tables are like a great big loudspeaker without cones. What it was is a big table that would be vibrated by a huge coil. In fact, they actually had a studio next door, almost like an AM radio studio, because of the amount of power that you had to have to these platforms. The problem is you're sending a signal down to represent a certain frequency and a certain amount of energy. Was that table really replicating what you wanted it to do? And that was sometimes a problem. So what they did is they had telemetry coming off of the table, instrumentation actually, coming off of the table back up to the analysis center. And by the way, we did something that we were way ahead of the industry, and I'm just fortunate to have a part in it. One of the guys got an idea. Actually, it was a team of the engineers at the Space Center got this idea about how to calibrate these tables. And so what they did is they came up with the idea of sending what they called a calibration pulse down to the table, and then looked at the data that came back and do a Fourier transform on that, on the data difference. And then what they would do is they would do an inverse transform to fudge the signal to compensate for that, so as to tweak it to get what they wanted. I was the only one writing the program, or I should say the support staff in machine code. So I wrote a special program. It took me quite a while to write it and test it and verify it. With, you know, we had a hard drive, which the heads never moved. The heads were either lowered down or pulled back up. There was no movement. So the heads literally floated, and I was only one or two people that was allowed to fire up this hard drive or turn it off. They were pneumatically lowered and raised. And then what happened is I used high-speed interrupts with high-speed buffering systems, because we would read the data off of the hard drive into a buffer, which went through a D to A converter down to the shaker tables. Then we had the data coming back from the shaker tables into another high-speed interrupt buffer system, to which I would then write as data on the hard drive. All this had to happen without any mishaps at all. And then I provided hooks in the program so the engineers could hook into that with their data drive and data read. And we were presenting papers on that, as Boeing was presenting papers on that throughout the United States, when NASA put out a question to all aerospace companies in the US to investigate the feasibility of doing this. And we had scooped the industry. So it was really neat to have a part in that. Okay, questions? This is all too simple, isn't it?
No, I don't.
I don't know about that.
No, I wouldn't say that, but Dave, how much inductance is in a straight piece of wire?
Oh my, depends on the frequency too. We used to say that skin effect. Oh, by the way, let's talk about skin effect. That goes into what you're talking about. It's in less than microhenries, but what happens is as current goes through the wire, let's say that we're reciprocating. The current is going in, changing, coming back, back and forth, back and forth, back and forth. Where is the magnetic field, the electromagnetic field, the strongest? Well, it's right dead center. And as since it's dead center, that means the conduction at the center of a conductor is zero by comparison to anything further out. The square law principle comes into play, so that as you move from the center of the conductor out towards the skin, you have more and more conduction. And that's why at really high frequencies, they don't use solid wires, they use hollow tubing. And then if you can go a step further and silver plate the tubing, then that takes care of more of the skin effect. So you have a better conductor on the outside. In terms of how much inductance, I frankly don't know. It's way down in the low microhenry.
Way tiny. Okay.
Oh yeah. Now there is one other thing, and that is as you coil the wire, each coil has an effect on all other coils. And so you have mutual inductance, and as a result of mutual inductance, a coil can, as you add coils, the factor goes up quickly. Hence the formula for inductance that you'll find in the ARRL handbook as an example.
Gotcha.
By the way, transformers, if you ever want to get into a discussion on transformers, there's more there than what meets the eye as well. Anyone know about magnetic amplifiers?
No.
Um, the Bismarck had magnetic amplifiers for their control systems. What we had was actually more accurate than the Bismarck, and what the Hood had was more accurate. However, the magnetic amplifiers that the Bismarck had were stable as all get out. A lot of the systems that both the Hood and as far as that goes, some of our ships, because I was a fire control tech in the Navy, those things, when you fire the 5-inch gums, tend to get out of whack sometimes. The mag amps never did. However, study of mag amps is quite involved. So
Nice.
rumor had that Boeing was looking at the possibility of using miniature mag amps in their missiles guidance system. And all of a sudden, excuse me, another instructor and I were asked to conduct a class on mag amps for engineers and engineering aides because they wanted to be on top of this. We spent the half of that class just on magnetic theory. I have run out of steam.
Nice. Thank you so much, Dave. That's amazing. I will do my new video editing skill on our recording here, and I'll include links.
Oh, there's something I can bring in. Can I do this?
Yeah, please.
In case you want to go down, if you're trying to explain something to somebody about phase angles, look at this. Now we're into Eli the Iceman, and we saw Eli. If the voltage rises before current does, that means it's an inductive circuit. This is pure inductive, therefore it's 90 degrees out of phase. That is, the current is 90 degrees lagging the voltage. In that same respect, if you go to the other one, which is Eli the Iceman, here in a capacitor, current leads the voltage. This is exactly what I was talking about on that power supply. So in a pure inductive circuit, the voltage lags the current by 90 degrees. Well, since you got a 90-degree lag here, and you have a 90-degree lag of the opposite values with coils, then you can see that between the two, you can have a 180-degree phase difference between the two of them. Then from there, we can get into things like power factor and such. There was something else. Oh, down here at the bottom, I think it was. Let's see, I think it was this one here. Let's do this guy here. Oh, okay. Here's something else I want to do. Twin T circuit. Let's do this. Take a look at this. This is a high pass filter. You can see that because the frequency has to be high in order to get through. This one here is a low pass because high pass gets shorted out. What happens if you combine these two together into one circuit? Here's your high pass, here's a low pass. What you have done is you have created a bandpass filter. And this bandpass filter was made famously by, in fact, Walt, correct me if I'm wrong on this, but I think this was the one that was the Hewlett-Packard tone generator. They basically used this kind of a thing here.
Yes, the early Hewlett-Packard oscillator that started the Hewlett-Packard company was a twin T oscillator circuit.
Wow.
It was real stable because they come up with the idea of using a incandescent bulb as the stabilizing factor. Now, let's go on a little bit further. Going down here to this guy. This is a twin T oscillator. They call it a Wayne bridge. And if you look at it, you'll find here, as you come out of here, you've got capacitor and resistor to ground and capacitor. That is the one I was showing you earlier. Here's your high pass filter. Then as you come out this way, this is your low pass filter. These two resistors and this capacitor. And if you pick the right values, this makes a beautiful tone generator for my Morse code unit. So what I have here is I have first of all, I have a transistor, a bipolar transistor. And of course, the phase difference between the collector and the base is going to be 180 degrees. So basically this circuit is just like the one I showed you previously. That is your oscillator right there. And then the output of the oscillator is fed through a volume control pump. That's a signal path coming through here. And that feeds the LM386, which is a unit that can run a speaker. And we have a MOSFET down here, and the MOSFET down here, by the way, this is not my design. This is a design I got from someone else. This guy here, this FET that's down here, would short this signal out. So the amplifier would not get this signal, but the signal would just crank away up here all the time. So when you build it, you go ahead and test this section here, and you make these adjustments in order to get the tone you want. I like 770 Hertz as my tone. And so then I feed that into here. And then this guy here can use, like if you come in here and at this control point, if you put a ground here, then the FET is disabled and full signal goes into this guy and you have a really nice tone. And the make and break on this is just beautiful. No chirping of any kind, just in and out. Very, very nice. So here's your twin T, and that's just like the drawing I showed you earlier. They depend on the value. So there are RC calculations to determine the resistance and capacitance of this here for getting you the right tones. Remember, you have a high pass filter and a low pass filter. You put them together with the right amount of shall we say, right frequencies, and you got yourself a band pass filter. So what you got here is an oscillator, which is really nothing more than an amplifier operating with feedback, and the feedback is what makes an amplifier an oscillator. That's something we always want to keep in mind. An oscillator is nothing more than an amplifier with positive feedback. Ta-da. The outfit that made this produced it as a kit, and I liked it, so I tried to get back a hold of them, but they went out of business. So I reverse engineered it and put it on my own circuit board.
Mm. Awesome.
So what do you think? It works great.
What's the other side of the control input, Dave? Is
This one here?
See on the very bottom where it says the
Oh, down here?
yeah, is it
Ground
that
or
ground
plus 5 volts.
or +5? Okay.
Yeah, ground or plus 5.
Okay.
In fact, one of the problems I have is when I first turn my keyer on, the keyer, that is the Arduino, comes up with a low. So this thing here immediately cranks out a nauseating signal until the Arduino comes over with its program, says, okay, we've got everything in shape. Then it goes high and shuts it off.
Gotcha. Nice.
So I have to come up with a solution for this.